The axolotl is my favorite animal.
As the world's most recognizable salamander, axolotls are not only cute but also possess impressive regeneration abilities. When an axolotl's limb is cut off, it can regrow an intact, functional limb in several months without showing a single scar.
No mammalian animals, including humans, can do that. As for me, I can only regrow my hair and my nails without any scars. To discover the secret behind axolotl's superior capacity for regeneration, let's first look at cell differentiation. A fertilized egg is an almighty stem cell.
It has the potential to convert or differentiate into every type of cell in the animal body. Nerve cells, muscle cells, liver cells, etc. Through development, stem cells do proliferate and turn into those cells, but not directly. They first differentiate into several types of multipotent stem cells, which further give rise to various specialized or terminally differentiated cell types. For example, mesenchymal stem cells are progenitor cells for cartilage, bone, muscle, and fat cells. This can be better illustrated using the Waddington's landscape model. On the top of the mountain sits the ball, representing the almighty stem cell. When it rolls down the hill, it can enter any of the several branching valleys and become different types of progenitor cells, which can also roll into more downstream valleys and become terminally differentiated cells. Scientists long believed that this process is a one-way street and irreversible until 2006, when Dr. Shinya Yamanaka discovered that a terminally differentiated cell can be reprogrammed back to a stem cell by overexpressing 4 transcription factors. Dr. Yamanaka won the 2012 Nobel Prize for this groundbreaking discovery. Now, back to axolotls. Scientists have found that upon limb amputation, the axolotl cells at the cutting plane turn back the clock and become de-differentiated. They escape their fates and become young again. As in Waddington's landscape, the balls at the bottom roll back to the intermediate stages halfway up the hill. Then, these new progenitor cells multiply. Eventually, they again differentiate into muscle cells, skin cells, blood vessel cells, or nerve cells, replaying the development process and rebuilding the missing part of the limb. This phenomenon is unique for axolotls and other urodels. In mammals, balls or cells at the bottom cannot roll back up on their own to the multipotent stage. Mammals' limited regenerative ability comes from a very small number of residual progenitor cells existing in adult tissues.
So, can we learn something from axolotls and use it to improve the clinical outcome for human patients?
The answer is maybe. One idea is that during trauma surgery, surgeons can treat the cells at the wound site with Yamanaka transcription factors in the format of working drugs.
By finding ways to turn back the clock of our cells, we may develop novel regenerative medicines. That is the lesson from those cute and magical axolotls.